All right, last time we finished off doing this like Newton's method thing, right? And it was pretty cool. It was like this fun iterative method that we wrote a loop to do to keep taking steps towards that value, which was neat. And we did that trick at the end to know when to stop. And the trick was, well, if we got the same value 2 times in a row, or if the difference between 2 successive executions was small enough, we're done. We're happy. Which is clever, but it's not something obvious. It's not something that anyone in this room I would expect you to know offhand. I'm just showing you these things so you become more familiar with what you can and what you can't do. Now, that right there, that code I wrote, which I don't even know if I have it saved. Let's see if it's saved. This one? Maybe. No, this does not look good, does it? Whatever. It's writing code to modify 3D printer files. Obviously. So I'll try one more. So it's not that. It's not assignment 1. Maybe this. If it's not here, whatever. I wrote that code to do Newton's method. All right, it's not here either. All right. That, though, is an example of an algorithm. Your assignment 1 is an algorithm. It's a word you've probably heard before, and it basically means the set of instructions you follow to do something. Just like a recipe for a cake, and I'm not being silly, like by definition, a recipe for baking a cake is an algorithm. I'm not, like that's not a joke, I'm not being silly, it is. But usually in the context of baking a cake, you don't use the word algorithm, you use the word recipe. Same with driving instructions. You don't use the word algorithm, you say like, well, here's the directions. But those are algorithms. Those are a series of steps you follow that if you follow them, will hopefully, if it's correct, solve that problem. And what's kind of interesting about algorithms is there are certain algorithms we will look at later in the course. I mean, all algorithms technically, but there are certain algorithms, for example, like a sorting algorithm. Raise your hand if you've ever had to sort anything before in your life. Put your hand up, of course you have, right? Maybe it's something you needed to sort alphabetically, by size, by color, whatever. You sorted something. I'm going to tell you something. Chances are that the strategy you used in your head when sorting is probably going to be at least one or a combination of a couple of sorting algorithms we will look at later in the course. But also, you actually, I'm going to almost guarantee you all kind of suck at sorting. But that's fine because the things that we're sorting is a small enough number that it doesn't matter so much. But there are some really interesting strategies for sorting that are just way faster than anything you've probably ever done before, which is really cool. But we'll talk about those later. But if we are following one of those example sorting algorithms that we will be talking about, it's kind of funny to think that if you follow this algorithm, you will have a sorted collection of things in the end. And that will beg the question, like, well, can we prove that? Like, why? Why does it work? And it becomes somewhat hard to answer that question in English because it's like, because it does, right? Like, if you just follow this algorithm, it'll sort the things. Look, watch, see, it works. But why? Because that's how our universe works. It's just if you follow those sets of instructions, you get a sorted set of things at the end. It's the way it is, because that's just how it works. And it's kind of funny to think of algorithms and what they accomplish is somehow connected with our universe, but it totally is. It's weird to think about. And I'm not trying to be all like, ooh, philosophy-y. No, it just is. So it's kind of fun. But anyways, those are algorithms. And the flip side of algorithms in early computer science learning is data structures. How do we store information in a clever, in a good way that works really well for a problem I'm trying to solve? And we will talk about some simple data structures. In fact, the ones we're going to talk about are lists, which aren't that simple. But if you're in 162 next semester, we're going to go into details on a variety of other data structures. And it's kind of fun. Like, we actually, in computer science, we love to make these really constrained things and see what we can do with them and see what we can't do with them. Because it's kind of fun to ask the question, like, well, I can't do this, but if I make this little change to how I'm doing this, suddenly I can do all of this. I don't know, computer scientists love geeking out about that type of stuff. This is all fairly abstract right now. As we get later in the course, this will be a little clearer. But there's algorithms and data structures. Algorithms are the set of instructions that you are going to follow to solve a problem. And the data structure is, well, if you're working with data, how are you holding onto that data? And is it a good choice for holding onto that data? We've seen some data structures before. Lists. There was a list of locations in assignment 1. When you split the stuff for the CAS problems, it creates a list. That's a simple data structure, but it's a really good one. It's like the most common one you're probably going to use. But your choice of data structure can affect your algorithm and vice versa. Like, if your data structure works this way, your algorithm might have to work that way. Or if you want to do the algorithm this way, well, you can't use that data structure really well, but maybe this one will work better. We'll skip this activity and just move on. So, strings. Strings are interesting because, you know, we've seen it as a type, right? We've seen integers, we've seen floats, we've seen booleans, and we've seen strings. But strings are a little different because a string kind of has like many values within it. Now, bear with me, because it might be weird to think about this, but if I give you the number 175, you might think, well, there's like 3 symbols there. But those 3 symbols mean one thing. It means 175. But if I give you like a sentence, right, it's kind of like, well, the problem is like, each of those characters and their ordering matter, but like they create words and it's kind of finicky. So you might remember a week or so ago I was talking about bits, right? The zeros and ones. And how we actually do have a finite number of zeros and ones we can use in our computers. If I have a 64-bit computer, you know, I can only have 2 to the 64 unique values that I can store in 64 bits because it's 2 to the 64 because it's just always multiplied by 2. Every time you add a new bit, you double how much you can represent. There is a finite number of things we can store in the computer. And what I'm about to say isn't going to be necessarily true for Python. Python is fancy, and it uses a lot of modern tricks, a lot of engineering fancy tricks. But let's go back in time a little bit and think about our computing systems in the past, in how they worked, before Python showed up and simplified stuff. Typically, let's keep it simple. Typically, if I want to store an integer, my computer is probably going to use 32 bits to store an integer. Just because. It uses 32 bits. 4 bytes. Raise your hand if you know what a byte is. I gave you a huge hint. Raise your hand if you don't know what it is, but you've totally heard that word before. Yeah. So, a single bit is like that 0 or 1. You could have 2 bits, 3 bits, 4 bits. You can have as many bits as you want. But if you have a set of 8 bits, we call that a byte. Does anyone know what we call half a byte? No? Who said that? Say it louder. A nibble. That's not a joke. It is. 4 bytes is a nibble. It's half a byte. Or no, 4 bits is a nibble because, you know, it's half a byte. So it's not a full byte. It's only a nibble. I didn't make that up. It's true. But anyways, let's say an integer takes up 4 bytes. Okay? But what we can think about is, well, you know, that integer, it takes up 4 bytes, but let's say, like, You know, the computer knows if I have an integer, I'm going to use 4 bytes to store. I'm going to use 32 bits. But let's throw the idea of 32 bits out the window for a second. And let's just think, if the computer wants to store an integer, it has like a nice, well-defined chunk of space it takes up in RAM. Because RAM is full of transistors that hold the low voltages and high voltages that represent zeros and ones. So even though, you know, it's 4 bytes, if I'm saying, like, for example, each chair represents 1 byte, you know, I could store an integer in those 4 chairs. But yeah, let's just pretend we store an integer in 1 chair. Each thing, like a Boolean, can fit in 1 chair. A float can fit in 1 chair and so on. Right? So that's how we store it. A single character fits in 1 chair. And in many programming languages, a character is its own type. In Python it's not, it's just a part of a string. But characters are their own thing. So you have integers, characters, booleans, floating point numbers. Some other programming languages we call those floating point numbers doubles, but whatever. So if I store an integer, if I say, okay, Python, I need you to make a variable for an integer. Python knows, okay, I'm going to go set aside 1 chair for that integer. And then whatever value I assign to it just gets to sit in that chair. Great. But if I come along and say, okay, Python, I want a variable for a string, we run into a bit of a problem. Because, well, how long is that string going to be? That string might be 1 letter, or it might be 700 letters. How big is that going to be? I can't just simply stick it in one of those chairs. It doesn't fit nicely in a single chair, like an integer or a Boolean or a float does. I'm in trouble. What am I going to do? So here's the solution. Is, okay, well, what we'll do is we will create a string of characters. Each character can sit in a seat. So if I have the string hello, H-E-L-L-O, I need 5 seats. So I can put the H-E-L-L-O there. So that's how we solve that problem, because integers have a fixed size. Characters, you know, have like a fixed size. But strings don't. They could be 5 characters long or 500 characters long, 5,000 characters long. They could be all those things. How much RAM does the computer need to allocate to that? It's got to put that value somewhere physically. So where's it going to put it? So that's how it came up with, that's how we solve this problem. So we go, okay, each letter gets its own chair. Okay? So that's the idea here. It's going to be similar to lists. Like we saw in lab, and maybe you were playing around with the lists in assignment 1. And we will be talking about lists in far more detail, I think, next topic. But it's the same idea with lists. Like, well, I have 1 integer that can sit there. But what happens if I need 5 integers? Well, I need 5 chairs. That's the idea. So strings are a little different. And what's really cool about strings is I can say print my string, and I see hello world. But I could also say, no, give me the character at index 2. So when I hit run, don't yell out the answer, take a second. When I hit run, think about what you might expect to see here. That's like saying, I'm asking for one chair, basically. And I've specified the 1. So on the count of 3, yell out what you expect to be printed out. 1, 2, 3. L. Who thought E? Because you're normal if you did. You did? But what's the catch? Computer scientists like start counting at 0. That's the funny little thing we do. So if I say 0, we get H. That's why. H, and then 1 is E, 2 is L, 3 is L, 4 is O, 5 is, what's 5? Space, exactly. It's there, it's just you can't see it. A space is a character. 6 should be W, and so on. So I can actually access individual characters from that string just by asking Python, well, give me the character at index such and such. And if you're having a hard time keeping track of, like, why do we start counting at 0? Remember, it's offsets. If I say my string starts at that seat. If I want index 0, I go offset 0. If I want index 2, I go offset 1, 2. So that's why it seems funny, but it actually makes sense. Kind of. So yeah, we are able to actually access individual characters from a string. So now, if you've got your computer, do this activity. Write a single line command to print the first 4 characters of some string A. Give that a go. Take a minute and try that out. Yeah?
Just based on what you said yesterday, I just got an email back from IT and Wikipedia works now.
Hey! Confirm it. IT lies all the time. It wasn't working this morning? Well, try it again. Try it again. And if you try and it doesn't work, make sure you hit like F5 or like refresh. Is it working for everybody? All right, well, it's working. Yay, okay. I wonder, raise your hand if you submitted a ticket. Aw, I was hoping everybody would. All right, well. Yeah, it's working now. It's working, okay, good. All right, well, try this activity, but thanks for the update. It was always working for me, but I guess it was just student accounts for some weird reason. God, if I don't have access to Wikipedia, I can't do my job. Yeah. Well, so there, I did it. You may have done it with like the concatenation, plus, which also works, but now it doesn't have the spaces between the characters. Cool. And then if I said print the second to the 7th, well, okay, so we go 2, 3, 4, 5, and I'm too lazy to write 6 and 7. Now I will say, if I ever say something like, okay, the first 4 characters, well, that's obvious, right? Okay, so I would want H-E-L-L. If I say second to the 7th, it might be a little ambiguous to you, because you're like, well, hold on. Do you mean the E or the L? Whenever there's ambiguity like that, I will do my best to make it not ambiguous. If it's during a lecture activity, it doesn't matter. Like do whichever. All that matters is that you can do it, not that, oh, you started at index 3, not 2, or 1, but not 2. You know, that doesn't matter. But if it's like an assignment or something, I will make it very clear. And if at any point you're like, wait, whoa, what do you mean? I'll just ask me and I'll tell you. But in this case, it doesn't matter so much. Now in Python actually lets you do a really cool thing that many other programming languages don't. It's called string slicing. So if I index 0, I get the E. But what I could actually do is say, okay, start at 0 and give me all the letters up to and excluding, not including, excluding 5. So that would give me 0, 1, 2, 3, 4. It would give me 5 things total, but indices 0, 1, 2, 3, 4. So that should be H-E-L-L-O. Perfect. This is called slicing. So if you put the colon in there, it basically means start and go to end, wherever you specify. Another cool thing you can do is you can also specify like how you count. If you add a third or a second colon and like a third number, if you say like 2, it'll actually like do every other character. Don't worry, stuff like this is like, I'm just showing you neat trivia. When would that be useful? All the time. All the time, but you'll see later. Yeah?
Why can't you use a colon for years?
Sorry?
Why can't you use a colon when you're doing the negative, like -1, -2 years?
You mean like this? You want to count backwards? Well, how do you go from 0 to 5 by counting by -1s? You can't, because you go 0, -1, -2. Am I ever going to get to 5? No. But what you could do is say, starting at 5, going to 0, count by -1s. That's the trick. I like what you're thinking, though. I think actually that's an activity later where I try to trick you. But now we've spoiled the fun. If you say 5 colon and you don't leave anything on the right-hand side, it'll just go to the end. Similarly, if you say colon 5, it'll start at the beginning and go all the way up to 5. It's cool. String slicing does make your life easier, because otherwise you'll have to do all this annoying indexing. But anyways, it's pretty neat, nice quality of life feature of Python. All right, so now let's do an activity. Now that you know that, okay, you've got a string, and a string is like a collection of individual characters. And you can access individual characters by indexing. By saying, give me the character at index 0, index 1. Here's what I want you to do. And this is a tricky one, but I believe in you. I'll give you like 5 minutes to try this activity. Write a function called vertprint. I guess it doesn't need to be a function if you don't want to make it a function. But write a function called vertprint that takes a string as an argument and then uses a while loop to print each character on its own line. See sample output below. Try this. Oh, I missed telling you something critically important for you to be able to do this. If you ever want to know how long a string is, ask it. If you want to know the length of a string called A, just say length of A. And if the string, I don't know, let's say A is whatever, it would say 15 characters long. This is going to be important for your while loop. Remember, if you get stuck, you can talk amongst yourselves and whatnot. It's always good practice. And assume A is a variable holding a string. There. So I've given you a little hint if you're worried about the length thing. Giving you just a little bit more of a hint. Raise your hand if you're done. Raise your hand if you'll be done in like one more minute. Just once. Okay. Oh, take the minute. Take the minute. There. Who had something that looks more or less like this? And, or who would have had something that looks more or less like this if I gave you just one more minute? Did people, so I saw people, a bunch of people were working on it though. What else did people use here? Let's take our time with this. What are we doing here? Well, we start defining the function and it's going to take a parameter to the string. And we have a while loop. And the while loop runs whenever the condition is true. And what is the condition we care about? Well, we want the loop to run for each character. And we also know that a while loop, okay, like this is clearly like a case where we're counting. So we're probably going to want a counter. Starting at 0, check whether the counter is less than something. We always need to increment that counter in the while loop, otherwise it'll run forever. But what we want to do here is say, okay, well, counter is less than the string length. Typically, I would probably write it like this. Just, keep it a little cleaner, because this will give me the length of the string. But it's kind of funny, right? Because, well, if the length of the string is 5, it's going to loop up to but excluding 5. Right? I'm saying less than the length of the string. But we always know when it's less than, if the string's length is 5, it'll never actually get to 5. It'll get to 4 and then stop. But this works just fine. Why? Because 0. We start at 0. 0, 1, 2, 3, 4. How many fingers am I holding up? 5. 5, not 4, because we count 0. And isn't it convenient also that like we start indexing at 0 as well? It's kind of handy. Works out pretty nicely. Now, the while loop is great and all, but there's another type of loop that you've all seen, assuming you did assignment 1. Anyone know the name of that other type of loop? If you do, yell it out. For. A for loop. Now, the for loop is kind of like for each thing in a group of things. So that's why it worked in assignment 1. You had a list. But the list contained latitude and longitudes. So you had a list of latitudes and longitudes. So that's why the for loop worked. We basically said for each location in the list of locations. So one at a time, it starts at the beginning, and it takes each location one at a time until it runs out of locations and it stops running. So that's why it worked really well there. Now here we could use it for a string. Because if we use a for loop for a string, it would basically mean for each character in this string of characters, which is, well, the string. That's why it's called a string, because it's like a string of characters. And we can do that to clean it up a little bit. So if we just go down here, I'll just replace it. So here it is with the while loop. Let's see what it looks like with a for loop. Okay, I'm going to get rid of that. In fact, I can get rid of this. For C in the string. Print C. Now, the difference before was when I used the while loop, I had a counter, and the counter was like a 0, a 1, a 2, a 3, 4, whatever. But that would then get us, that meant like the index of the string. So we had to take the string and ask the string, okay, give me the thing at index whatever the counter was. First time through the loop, index 0, then index 1, and so on. In this case, we don't have the numbers. We have the things. So I don't have to index anything. I could just say, for each C in the string, so that's each character. Every time through the loop, the variable C will be a character, starting at the beginning, going to the end. You might say, oh, does it have to be C because it's a character? No, we could call this whatever we want. And it'll work just fine. I do not recommend this particular example, but it works just fine. So for each thing in a collection of things, that's what you think about. Now, this might be weird to you. And I know that, you know that rabbit story that I told? One of the big main things for me at that time was these for each loops. It was a different programming language, but for each loops gave me a really hard time. I like something that was more closer to that while loop, that counted. But whenever the for each loop came in, I just couldn't wrap my head around it until it finally clicked. So if you don't really like this off the bat, you're normal, you're like me. But they are pretty handy. And we will see the for each loop come up in other instances as well, later used slightly differently. But here's an alternative way to do the same thing. Are there any questions about this for loop here?
I'm just a little bit confused on why like C works, but I just don't understand.
Oh, why C, right, instead of having to index?
Yeah.
It's because if I have the string, I'm going to put it back to C because that's a reasonable thing. Maybe it's called like CH for character, I guess. So this is the string it gets. Basically, here's how this is going to work. It takes this, Python will take this string, and you know what? Here. So for CH in, I'm going to hard code a string in there. Maybe it won't let me do that. Okay, perfect. There, I've hard coded the string in there, so it's not a variable anymore. But we will see that the string, so this says for each C character in this case, because it is a string. So for each character called CH, in the string hello, I want you to print out that character. We start at the beginning. So the first time through the loop, CH will be assigned the H. Print out CH, we CH. The loop finishes and then starts over. Goes to the next thing. It's E. CH becomes E. Print out the E. And so on and so on and so on until we print out the O, and then we go up and go, oh, well, there's no more things left, so we stop. You're right for being like, but what? Because a moment ago we had to index the string. And you're right. I'm going to show you something. With the while loop, because I had a counter, that counter only counted. It only could represent. I'm going to switch the for loop just slightly. So here is this for loop. I can do it slightly different. I'm just spelling it out better. Enumerate. Okay, don't worry about memorizing this right now or anything. We'll talk about enumerate a little bit later. But when I write the for loop this way, instead of saying in string, I said in enumerate string. And instead, what it's going to do is say, it's going to give me two variables, index and character. Index will be what index the character is at, and character will be the character. And every time through the loop, both those values will update. So let's have a look here. I can print out index and character. Okay, we don't need this. There. Okay, 0, H, 1, E, 2, L, 3, L, and so on. I guess it's just one more. Even more, watch this. I could say, okay, I'm going to take this out and actually make it a string. No. What? Oh, okay. No. Where did it go? All right, well, whatever. I'm just going to use I and C. Enumerate the string. Nope. Print I, C. Okay, we're back. So I'm printing out the index and the character as we go. But I could also do this. Nope. I. So I'm saying print out the index, print out the character at that index, and then also take this whole string, but only give me back the letter at that index. When I hit run, think for a second about what you expect to see. Don't yell out the answer, just think. Take a second, look at this code. What would you expect to see here? If I is the index, 0, 1, 2, 3, 4, 5, and C is H-E-L-L-O, what would we see here now? Okay, raise your hand if you have an idea in your head. Okay, I'm going to hit run, and we're testing you because you asked the question. Is that what you expected? Yeah. It's because we have an index, we have an individual character, or we can take the whole string but ask for only one of those characters. And that's what we kind of did there. Because. Yeah.
Why does it add to the index each time it wants to go?
Why does it add to the index? Just because the I is, I'm not sure what you mean. So why does it add to the index? It's just keeping track basically like how many times the loop ran basically.
But like, why does it add 1 and then move on to the other character every time it runs the code it goes to the string? Like, for every time it runs, like, it'll go with H with 0. Why does it add 1 to go to E next one?
Why does it? Because that's how the loop is like designed to work. It's like, okay, do the first thing, and then when you're done, move down. Do the next thing, move down. And moving down here means like incrementing I and moving the character to the next subsequent character. Think on that, and if you're still puzzled with it, ask again on Friday and we'll clear it up. Cool? Okie dokie. All right, see you all later.